In some of our previous videos we've had a look at current and charge, and we've discussed how current is the flow of charge around our circuit. And today we're going to have a look at what it is that causes this charge to flow around a circuit, and we call that voltage. There are two types of voltage which we're going to have a look at. Both have abbreviations. One is E.M.F and one is PD. And a little further through this we'll have a look at exactly what that stands for and what the difference is between them. We're also going to have a look at how we measure voltage and an equation which we use to link charge with voltage. So we'll have a look at the unit first, because that makes it easiest to describe exactly what this voltage is. And voltage is measured in the volt, and 1 volt is defined as 1 joule per 1 coulomb. So 1 volt is 1 joule per 1 coulomb. So it is an amount of energy per an amount of charge. So we'll see which way that energy is going later. This energy per charge is quite crucial for the subtle yet very important difference between the E.M.F and the PD that we saw before. So let's sketch out a simple circuit to try and illustrate what's going on here. So I'll just do a cell or battery and connect it up to a resistor, and the direction of conventional current will be flowing around in this sort of direction, so that's anti-clockwise as we're looking at it here. And so we have this charge flowing around the circuit, and as it does so it's going to gain and lose energy. So this resistor might get quite warm, so there's some thermal energy being dissipated there, which means energy must be coming from somewhere. And similarly this battery gets depleted, and so there must be some energy coming from somewhere into something, which then gets carried through the circuit to the resistor to get dissipated as heat. And so this is what this voltage is. This is this energy per coulomb. So these little electrons, so these electrons which are flowing around the circuit, of course, because they're electrons and conventional current is the flow of positive charge, the electrons will actually be flowing the other way around, so they will be travelling this way through the cell and this way through the resistor. As they pass through the cell, they're going to gain some energy, and as they pass through the resistor they're going to lose some energy. And this is what a voltage is. It's how much energy we're giving to or taking away from each coulomb of charge that flows through some component. And this allows us to go back and have a look at these definitions. So the first one, this E.M.F, stands for electromotive force, and this is when we're putting energy into the circuit. We define electromotive force as the energy transferred per unit charge, so we were saying joules per coulomb, energy per charge, energy transferred per unit charge when one other type of energy is converted into electrical energy. So we're going from some other type of energy into the electrical energy. We're putting energy into the circuit. So in a cell this is going to be from chemical energy into electrical energy. We might have something like a photovoltaic cell which is going from solar energy into electrical energy. And there's other ways that we can have, for example, a dynamo would do kinetic energy into electrical, so on and so forth. The opposite, where we're taking energy out of the system, is what this PD is. This is the potential difference. So this is when energy is transferred, energy transferred per unit charge when electrical energy is converted into one other type of energy. So we're going from electrical into another type. So we might be going into thermal energy in a heater or a resistor. We could be going into kinetic energy in a motor, so on and so forth. So we can see that this electromotive force and this potential difference are extremely similar, but there are the subtle difference is extremely important. One is energy being transferred into electrical energy, so energy going into the circuit, that's the electromotive force or the E.M.F, and the other is electrical energy being taken out of the circuit, being transferred into some other type, and that's this potential difference or PD. So if we've got voltage as being an energy per charge, then we can now introduce an equation which we can use to say, okay, if we've got some amount of charge flowing around a circuit and we've got some voltage, so an E.M.F, and we want to know how much energy we're putting in, or we've got a potential difference and we want to know how much energy we're taking out, this is the equation which we're going to use. So this W is work done, and that will be in joules, so that is the work done on the charge if we've got an E.M.F, or the work done by a charge if we've got a potential difference. So if we're doing work on a charge, then we're giving it energy. If work is being done on something by charge, then that charge is going to lose energy. So then here we have that voltage, and that will be in volts, and here we have the charge, and that will be in coulombs. So we can see a fairly straightforward equation which allows us to work out how much energy is being either put into or taken out of a system, depending on whether we've got an E.M.F or a potential difference, when we're looking at some given amount of charge. And so we'll just have a look at a straightforward example here. So in an electron microscope we have electrons whizzing around. In this question we're going to look at a single electron, and it's being accelerated across a 5 kilovolt potential. Determine the amount of energy that the electron gains. Now this sounds like it doesn't immediately have anything to do with the circuits that we've been discussing, but we can still see that if we've got an electron moving across some potential, moving across some voltage, then because an electron is a charged particle, then we're going to have that amount of charge gain some energy because of the voltage as dictated by the equation we just saw. So W equals VQ. So the electron has some charge, and the charge on an electron we know is 1.609 times 10 to the minus 19 coulombs. And the voltage that we're accelerating across is 5 kilovolts, so 5,000 volts. That's from the question. And so we can determine exactly how much energy this electron is going to have after reaching the other side of this potential, and that will likely be in some form of kinetic energy. So once we've worked it out, although this question doesn't ask for it, if we wanted, we could work out how fast the electron was travelling by the time we reached the other side. And so this is actually extremely simple. We just multiply these two numbers together, and what we get is 8.011 times 10 to the minus 16 joules. So quite a small amount of energy, but remember this question is only asking us to look at a single electron. And that's how much energy this electron will have due to being accelerated across this voltage, as per the equations which we've introduced. So that is what a voltage is. This is what causes this current to flow around a circuit. This is what drives the charge to flow. It is given energy, and then energy is taken away at some point further down the line. So it is given energy at an E.M.F at a cell, for example, and then further around the circuit we take that energy back out, which is the potential difference, and we measure it in volts.